Hello everyone, welcome to this session. In the previous sessions, we have already known how PSO works. So in this session, we will talk about how to implement PSO. Fortunately, there is a built-in function of PSO in MATLAB, and now let's see how to use it. The function simplest form, like GA, x equals to particle swarm function, number of variables. So we can see again, this function carries out minimization and no constraint is considered. So the x is an optimal solution after the optimization. Fun, this is an objective function, and NVRS, this is the number of design variables of this function. Simplest form like GA, right? So the next step is what? According to the GA experience, we hope to add a lower bound and upper bound. So this is the format with LB and UB. So in this case, the search bounds are considered. The X functions and the NVRS, they're the same as before. And LB is a lower bound of the decision variables, and the UB is a upper bound of decision variables. One thing that is different from GA is what? Is there is no empty square brackets when we put the upper lower and upper bound. For those ones, the empty square brackets are for what? Are for constraints, right? So the built-in MATLAB built-in particle swarm optimization haven't considered the constraints yet, but how to use this function to consider constraints? We have a method, so that will be covered in the next specialization, the advanced course. So welcome to that. So here, we can still put options here. So the optimization settings, such as the PSO parameters, and how can we plot, this can be put here, right? So we can see the options is still a struct like GA, and we can also set it by the optimum options function. So this time, it's not GA, it's particle swarm. It means we put it here, we can plot. For example, this one plot the convergence curve. Right, we plot the PSM plot best F. This one you plot the convergence curve of the PSO. And we can see the output. Clearly, I think you can guess, right? So the FVL is for what? Is for the objective function of the optimal solution, right? So there are two other things, the exit flag and the output. So in fact, this one also exists in the GA function. So let's see briefly what are they. An exit flag is a value to tell you that when the algorithm stops. So why the algorithm stops? So we can see here's a table. So I just explain some of them. So first of all, we can see the relativity change in the objective value is less than options dot function tolerance. So this is telling you in the options function tolerance, you can set a value, right? So if it's smaller than that, this means what? The objective function does not improve for a while, then I terminate it. The second number of iterations exceeded the options max iterations. This means I set a certain number of iterations according to computing budget or my patience, right, as a stopping criteria. So later on, you can see the following, right? So some of them we are not covered in this specialization. That will be the advanced one. And output is a structure. This contains the information of the whole optimization process. So it has several properties, such as the iterations, the number of iterations the PSO solver has used, and the function count, the number of objective function evaluations, and the reason for the algorithm to stop, and about the random number used. And here is one, we call it a hybrid flag. So this one, we call it the exit flag from the hybrid function. So this relates to hybrid function objects. So what are these? So hybrid function means that PSO, we know that this is a global optimization function in the global optimization toolbox. So sometimes when we, after a global optimization technique, we may want to further improve it locally. So we can do a local optimization using the optimal result of PSO. So for example, we can use a FME search, pattern search, F-mean UNC, F-mean com. So these functions are the conventional mathematical optimization algorithms, and they can use it to support the PSO. So PSO can first globally jump out of many local optima to find a satisfactory solution. And these methods, we can use that one as a starting point to make a further improvement, right? Another thing that we can talk about, also applies to GA, is a parallel computing. Because all the population-based algorithms, they need to calculate too many objective function evaluations. There's a population there. And these could cost a long time because it may involve simulations, right? So in this way, the parallel evaluation of the objective functions of the population, this becomes important. So using parallel computing, we can simultaneously evaluate these objective functions of a number of candidate solutions. So the maybe 10 solutions, optimization time as the evaluation time will become 1 if we can parallel them, right? So in this case, we can set optimal options, use parallel equals to true. So this one will carry out the parallel computing for you, right? So more details, we can see the MATLAB parallel computing help, right? So that's all for this session. Thank you very much. Bye-bye.